department or why isn't any faculty, teaching it? So is it that students are not willing to, push the department to learn it, or what's happening?
Sir, we did force the department. We made a DUGC committee to handle these issues, and we are currently in the process of adding these courses to our department. Because as you know, the course structure has been changed a lot, and like now the second year guys are actually till now studied mostly everything that we have studied till now. Like with the third year, they are on par with the third year right now. So we are
so they know advanced reservoir engineering and all that.
Yes, sir. Basically, logging has been taught to them, and both the reservoir courses, I guess, have been taken. So their final year will be pretty empty. So there will be many slots available. As I guess it's not compulsory for them to study mathematics for four more sems or mechanical, all those subjects.
Yeah.
We are currently under process to add new courses such as machine learning and all that.
Okay. And can people raise hands who are interested in reservoir simulation, about learning how to make a reservoir simulator, or who are interested in reservoir engineering? Can they raise hands and just have a look at the participants? Okay, that's good enough. 8, 9 students. So that is half the population of participation. Okay. Yeah, it's fine. You can keep your hands down. Because I was thinking that we are taught reservoir engineering and we are taught reservoir simulation basics, but students should know how to make a reservoir simulator, maybe using Python or MATLAB, and it's much easier in MATLAB because the library already is existing, and it's just easy to pick tools from there and make it. Think about it. Maybe I'll talk with the chapter again, or we can open course about it. Okay, I'll share my screen.
So there is one doubt in the chat box.
Okay. Yeah, tell me.
Yeah, guys, you can unmute yourself.
Yeah, sir. Just in pair plot, actually, that video which you shared, he told us some kind actually after the data parameter. We can put a kind for regression KDE with this line chart. And when I was referring to your Jupyter file, then you have used diagonal kind.
Okay.
So it basically changes the whole diagonal, making it histogram. But how to change the rest of the both triangles, upper and lower? Is there any specific function for that?
You want to change the nature of triangles and other two parts of the plot, right?
Yeah.
So pair plot is actually a scattered plot which is made for all the variables. I don't know because I haven't used histogram for both sides, because scattered plot makes more sense. You want to have a look at the variable and how are they behaving with respect to each other, and scattered plot makes more sense. I don't know how will you like to understand the variation between data points of two variables using histogram. So basically histogram for the same variable. Just a minute. we use histogram in the cross one because we are trying to map the same variable, and histogram makes more sense because then you can understand the variation of that variable uh, with respect to the bandwidth of these data points. You understand my point? Like if you remember Wallen plots, it's a plot between the data point itself with respect to the the bandwidth of the set. So we're understanding the single variable using Wallen plot or box plot and histogram. So that's why it's like you can understand why it's diagonal. But as far as you want to understand variation between two variables, scattered plot makes more impact and it's easy to analyze it. You can get histogram. There'll be some other plot or some other parameter that you need to tweak. You can send me an email. Maybe I can have a look at it after the workshop, and then I'll tell you how we can get the histogram.
So basically, if we write kind, in the video also, kind was only changing the ones on the diagonal. Rest both remained scattered, the upper and lower triangle in the matrix.
Yeah.
So, okay.
So let me explain you what I said. I think you didn't understand my point. So, okay, I cover this point when I go through the worksheet, and then I'll tell you when we encounter this plot again. Okay, remind me in the chart.
Sure, sir. Sure.
Okay. So yeah, I think we are done with data visualization, pandas, data frame, numpy library, and understanding the basics. Let me know if you guys are facing any problem with understanding, and there are a lot of resources that you can practice on. There's W3 schools, if you want to learn basics towards data science blog, a site that has a lot of extensive, documentation of the libraries and all the experiments people do. You can do that. I've told you before, but I'll tell you again why we do data preprocessing. So you must have seen the box plots and the Warden plots that we were watching yesterday. That you can see the data was not, spread out uniformly, and there were patches of the data. The data was varying with the value too much. There is also variation among the variables. So for example, we have three variables A, B, C, and A goes from 0 to 1, B goes from -1 to 1, and C goes from 100 to 1000. So this is the variation in the values I just told you. So you can understand that when machine learning is actually, using equations and trying to fit in an equation in that data set. So if you're taking like a linear equation, ax plus by equal to c, like for two variables, the weightage of b would be different from weightage of a because the values vary from different range. Maybe one is a is from 1 to 100 and b is from 10,000 to 1 million. So you can understand the amount of weightage b will have in the equation, and a will have less weightage. So it can really change the algorithm when you're trying to fit the equation. So what we do is we have to normalize the data. We have to get all those values in similar bandwidth, maybe from 0 to 1 or -1 to 1, from 0 to 10, depending upon what's the situation. We have to normalize the data. We have to scale the data. We have to remove the missing data. We have to fill in the ambiguous data. We have to remove the outliers. And yeah, so these are the topics that I'll be covering this today, which would be scaling, outlier detection, and cross-validation and types of error. Types of error is actually just basic mathematics and a few terms that I'll explain you, and I've provided link at the end of the notebook, so you can just have a read at it. It's not a rocket science. And then first will be scaling, outlier detection, and cross-validation. So uh, just a minute, I'll be back in 2 minutes. So yeah, uh, we have well 13, 14, and 15 from the Valve data project. This I told you this yesterday. So let me clear all the outputs. Okay, so we load this data, and then so if you had a look at the data, we have well 13, 14, 15. Well 14 and 15 have all the values with their faces. And well 13, all the variables are given, but the target is missing. The aim of this project, which I would be teaching after in the last day, would be to use well 14 and 15 data to run the model on that, to train the model, and then implement that model on well 13. So that's the aim. So well 13 has all the target values missing, well 14 and 15 have all the data, including the targets and outputs. So by concat, we mean we are merging the data of well 14 and 15 together. And we created another column named as well, which would be segregated. So we have, given the name of this well as 14 and 15 using this as that category. And then we have standardized the RT values with log 10. So this is a basic standardization. I'll make you understand what's the the formal method to standardize data. So you can see RT data after applying log is down to and 0 point digit values. Now, I didn't explain you what is these variables mean for. It's gamma radioactivity, which is GR, and all these data can be retrieved from the logging data. We have total resistivity, density, neuron porosity. Facies is actually the type of rock. It can be sandstone, carbonate, or any other type of rock. And RT is the resistivity, total resistivity of the formation. So Preet told me that you guys have some knowledge of logging, so maybe you can relate it now that we have all this logging data, and now we try to classify what kind of rock is beneath. Now we try to plot the facie of the well. So let's have a look at the pair plot. It takes time to load, and till then I can go through this. Okay. So okay. Now, one student asked me, why is it histogram and why is there a scattered plot? Now, if you can see, GR versus GR plot is a histogram. And okay, let me zoom in. So GR plot versus GR plot is a histogram. RT plot versus RT plot is a histogram, and resistivity plot, the porosity plot, neuron porosity plot, and the RT plot is also a histogram. So why is it a histogram? This is because you're trying to understand the variation among data in a single variable. If you remember, you need to have an understanding of how this data set is varying. Is it too extreme? Is it just like the last time the data we had? Let me show you. So you see the data here is it's not uniform. The downhole pressure below 200 is nothing, and the maximum density lies between 200 to 250. This kind of data is not preferred to train because the more uniform is the data, the better versatility will have in the model to run. Your equation needs to, in short, what I said is that your equation or your function that you are trying to fit in these data points should have the knowledge of what other points can, it can encounter. If the equation is just used to from 200 to 300, and if there is a pressure point which is less than 200, your model won't give a good accuracy. So that's why you need data pre-processing to understand that. Okay, now I think the point was clear that we need to understand the variation. So this is just to bias data. The model will only know about points which are in this region. What if it exceeds? So now this kind of data is very good because there is a uniformity among the points, and the mean is kind of in the middle. So you have a good variation among data points from the mean median itself. There must be other things that you can observe, that there are some points which are kind of outside the box, outside the group. These are called outliers. Not all points which are away from the group are outlier. There are many methods that I'll teach you, which is which helps in removing the outliers. So these are the outliers. You can see the uniformity. This is a uniform data set. This is too biased. So we try as much as possible to make a uniform, standardized, outlier-free data, with no missing values. Now, I also, so if you see the data of well 14 and 15 together, so I've added these wells, and you see faces here, right? Now I gave the faces a number like 1, 2, 3, 1, 2, 3, because your equation needs to have the output in numbers and not string, because it's a mathematical equation. There are other ways that you can work with these alphabetical output, but then for now I'm converting it all to variables so that you can have a better understanding. So we have three kind of faces: SH, UN, and CB. So I gave all the number, and there is one more SS, which is sandstone. I created a list library which has 1, 2, 3, 4, and I gave the numbers to each facey now. And then now you can see we have faces labeled. So SH is 1, UN is 2, SH is again 1. So I've given the numbers now. You'll understand it later that why number is necessary. As I said, we are training an equation, so we need numbers. Now so this is a kind of algorithm that I haven't built. I took it from a research paper, which is based on facie classification using machine learning. You can understand this line by line. And if you are facing any difficulty with understanding the code, you can let me know. So facies color, so this is the color code we are going to give to each variable. We have the facies name, and we make a function name as make facies plot, which will have the value of logs and facies color as input. Now logs, we create another variable which will have the values from this chart, these 4 variables, which is for whom we have defined the color pattern also. I can go line by line. I'm not going to tell you how this function is made. Then we try to plot it. So give it some time. Now we have made the function here, and we feed the data of well 14 with the color pattern that we have mentioned at the top. So this is a very interactive plot that, which has, it's kind of amazing to see that we have actually plotted the whole logging data in Python itself with just two functions we have. So here we have GR, which you can see there is a variation. You can see RT, neuron density, and feces also. So I'll give you a bigger look here now. You can see the rock types are changing with the depth, and this is the depth from 3,200 to 4,200. And you can see the depth, how it is varying. Like, we have SH here, then we got sandstones in between. We have CB, which is carbonate layers. This is the major carbonate layer, and then we have some small layers, and how this rock is actually varying with depth. This is very informative for me, at least, to see how the values are varying. And I can see how neutron density, the gamma rays, the resistivity values are varying. You can see there are some big values here, which are like outliers because they don't match the trend. Every data here has an outlier. So even GR, this value is too big. There may be some problem with the data acquisition or, reading the values. So you can see here is an outlier. The values are varying. It's the RHOB is from 2 to 3, and GR is from 0 to 500, RT is from 0 to 1. So you can see how the weightage of these values are different when we try to use them in an equation. So let's have a look at how the facies are varying with respect to the log in each well. Okay. So SS has the maximum, carbonate has the maximum value in the facie. It takes the data point and then, tries to map according to the histogram with the number of values. And then lowest is LN. Now we set the index as depth. I told you last time why it is depth. And we group the data together with respect to well. And we see the values of both the wells together now. There is also a statistical function named .describe, which gives you the mean, standard deviation, minimum, maximum, and the in quartile range. In quartile range would be needed to understand how standardization is done, how scaling is done. So you can have a look at the statistics from this function. Now, so you must have got by now that these are the 4 variables for us, which we will be using to calculate the facies classification. So we are doing facie classification here now. And this is the target variable. So we use these 4 values to define the facie. And this would be assume our X, and this will be our Y. So that's what I've done. I have segregated the data set now into X, where I have dropped facies, well, place label, and RT log, and Y is a facie. And then, so this is an important, important milestone in our workshop. We have reached to the point where we have learned about XY, target feature, data preprocessing, data visualization, and now the basics of machine learning starts and how this algorithm is made. So what happens in machine learning is that when you have, suppose, 100 data points, you divide those points into testing and training data set for basic. And then you try to run your model on the training set. And after that model runs on the training set, you try to fit into the testing data set so that you can understand the accuracy of your model and the errors in your model and how precise is your model on training set. So generally the data, the distribution is 70% to 30% or 60% to 40%, depending upon the number of data points you have. So 70% is the training set and 30% is the testing data set. As you can see here, I'm using this function test train split, and I got the library in the first itself. All my libraries are here. So I use sklearn. It's another library which we use in machine learning and also in pre-processing. So this sklearn is totally related to machine learning and data science, deep learning and stuff. So from there, I import test train test split function. I feed the X and Y. I give the test size to be 0.3, which is 30% of the data set, and random state. So what is random state? Random state is that generally when we feed the data, it's from the same structure that I've given already, 0, 1, 2, 3. Now, if I give random state, it has its own algorithm to divide those points randomly and then feed the data to this function. So that's what is happening. You can give some random state value. I generally give it a higher one because I need more randomization. It can be, it actually doesn't matter as long as it is some good finite value. Now we see the dimensions of X train, which is the training set of all the the variables X that we are using. And then we see the dimensions of X test. So this is kind of 30% and this is 70% of the whole data set. We can have a look at the training data set, histogram values, the variation here. And we can have a look at the X test and X train. So here you can see how depth is, random instead of a structured way. We need to randomize our data set because we need the model to be versatile, as I've said before. So it's all random here now. This is 30% of the complete data set, and this is 70%. We have the 4 variables. And now you can see the difference in values. This is, in hundreds, 1, 2s, and this is 0 point values. Now we do scaling. So scaling is normalization, standardization, all are same. So all mean the same. You're trying to uniformize the data. You're trying to give them a range in which all the data set can fit in. You can use mean. There are different kind of algorithms. Again, there are like 10 to 12 algorithms on which you can try to scale the data, normalize the data. You can have a read at it. And this scaling is done before we do the training of the machine learning model. This is a part of data pre-processing, and you can just see from the data that how the bandwidth is varying. Now there are some types of scaling methods: min, max, standard, maximum, max, robust scaler, and there are more. I just gave you 7 basic ones. I generally use robust scaler because it has it has a lot of it has a lot of good it has some good points that it overpowers the other scaling functions. Like robust scaler, there is no high memory requirement. It doesn't store a lot of data in memory and tries to process it. It needs very less computational power, which is good for students, and it works well with all kind of data sets, and especially data sets which are very large. And being in petroleum engineering, we need to use functions which can handle large data set. I mean, right now it's just 3,000 points. Assume you learned all this and you are applying into a company or some competition or something which has 10,000 data points, or maybe 1 million. That's where you need to have robust methods to scale, which is robust scaler. Now, all these functions, they vary with their algorithm of how they are scaling the data. So this is the basic one. min-max scalar and standard scalar. Min-max scalar is actually taking the mean of last and first value, creating that standard deviation and dividing it with all data points. So that's how it's scaling the data. And then we have standard scalar, which is the mean error value divided by the standard deviation. Now, I'll introduce you robust scalar. You can have a look at the algorithm of robust scalar. And actually, you don't need to have the knowledge of each statistical algorithm in data science or machine learning. But you need to know what makes it better, which function to use, which scaling method to use, and that comes with experience. And trying all kind of tools in that. So you can just create a function, which has all kind of scaling methods, and then see how the data is varying. Maybe plot a pair plot or a histogram plot and see how it's varying. You can try that as an experiment to see how and which ones are creating more impact with scaling. So we use robust scalar now, which has a complicated exponential algorithm to standardize the data set. And the good thing about robust scaling is that it gets the data set to a very have a look here. So I'll take you step by step here. So we store the value of robust scalar algorithm in R scalar. We fit the X-train data into that algorithm. So now we have a function which knows the value and which tries to fit in with the X-train values. And then we transform those training values using the scalar model we have trained here, and we get X-trained scale data. We store these scaled values of X-train into this variable X-train scaled. Now we can see the median, the quartile range of the X-train scaled of the model itself and the scaled model. You can also have a look at the 75 quartile range. It's not needed, but if you have a little bit of knowledge of what is in quartile range, mode, median, you can understand what's happening here. So it's just for your reference. You don't need to do it every time to understand what's happening. And then we need to also transform the X test to X using scaling method. So now we have divided the data, we have scaled the data to using the robust scalar. And now you can see we have feeded this training data into pandas data frame to have a look at it. And you can see the values are now between -1 to 1 with very high values barely going outside 1. So now you can see we have scaled the data from -1 to 1 and near about. Now you can see there are some very big values here, right? Maybe larger than that in these 973 points. Now we need to remove the outliers. So we have scaled the data, we have split the data into training and testing, and now learn what's the isolation for it. So outlier detection is just like as I said, you have these abnormally large values, and we need to remove them because your model, your equation would be influenced by these very high outlying values. So it's just like saying that your equation is kind of straight line here, but then because of these 2 points, it may have some inclination. Maybe your graph is like this, but when your plot reaches to this region, it will just rise up, which is not the actual case. So we now need to remove the outliers here. So one good method that I use and I have seen most people using is isolation forest. Again, you don't need to know the algorithm, but for your curiosity, I've shown you the algorithm here, which uses the mean distance from the the median of the cluster. It finds the average distance, and then on the basis of that, it segregates using the average mean distance from all points. You can learn more about this using this link I've given to understand how isolation forest algorithm works for outlier detection. I've also written the basic equation and what does it mean. Now again, we use isolation forest function, which is also in sklearn library, as I remember. So yeah, sklearn ensemble isolation forest. So we create a template for isolation model with number of estimators as 200 and contamination as 0.5 to 0.5 by 100. So you really don't need to know what's contamination. It's a conventional value that we use as a sorry. Uh, we now have created a template of isolation forest model, and then we fit this model into training data set to find the outliers. Then we predict the training. We do the prediction in the sense that we try to predict what's the outlier, what's the normal data set points, and what is outlier. Now, after segregating and predicting the outliers and uh, the normal points, we try to plot it. So you'll have a better understanding of what I'm trying to say here. So uh, this is X-train, which has outliers and the normal points predicted. Now you can see how X-train is varying actually. So this is the normal values, orange one. These are the normal values which are going through the trend. And now you can see the outliers. They are in blue color, how outliers are behaving. They are kind of very far away from data set. And it's also that we can decide which outliers to remove. So I feel this outlier, that this function is fine. We don't need to remove this one or this one, maybe these 4 or 5 points, because we are losing data over algorithm. So we can also decide which outliers to remove, which we'll have a look at it further. Now we'll remove the outliers. So we use that by comparing it to the Y train. Y train is the target. Now you must be having gaps of knowledge that what's happening in this line, what's happening with the outlier, how is it, what's fitting, what's training, what's transformation. So I'm telling you all these keywords so that you can start, working on how you can learn yourself, because I cannot teach you everything in 5 days. Like it's very even I can just choose, outlier detection or scaling method and teach you for 6 days continuously, and there'll be still something that you won't understand and I'll miss out on the content or the concept. So that's where you need to start doing it on your own. What is as type category? We use it to, categorize the string. So if you break down this code step by step, you can see after applying as type dot in quotation category, we got these values. We have categorized the data into 0, 1. using Outlier. So that's the thing that is your homework every day. And now we see the length, and now we see the visualization without outliers. We have removed it according to this algorithm, which actually compares the x values with y values. So if the y values are kind of matching with the trend, then it's not removed. But if y values, maybe it's a bunch of sand carbonate, maybe carbonate layer, and then you see some points of sandstone. So you have to remove it. So that's how it's comparing. It sees a feature and it's like, okay, we have 5 points. Now what? Should we remove or not? Remove it or not? And then for this question, we go to the y value. And we are like, okay, 3 points are kind of matching with the target, and 2 points are not. They're not even matching with the target with the rock petrophysics. Okay, so let's remove two. So that's how it's happening. Now we see visualization without outliers. So see, not all are removed, but the major good ones which will distort the algorithm are removed. You can compare these two. You can save the image, keep it side by side, and see what's the difference between them. So now what has been done? We split the data, and we have normalized the data between 0 to 1. We have removed the outliers. We have got the data into pandas data frame. We have replaced all the missing values using mean, mode, median, depending upon what's your choice. Generally, I go for mean. And now we do cross-validation. So what happens with cross-validation is that sometimes we don't have enough large data. And suppose you have just 10 points and you are like, okay, I can do the training and testing splitting, but our model will have really less data points to train itself. So we create random data sets using some value from training and testing. So we can choose how many cross-validating data points we want. Suppose I give cross-validation as 10, which we'll have a look at in the next session about regression and machine learning project. Suppose I need 5 data sets. So I take some points from training, testing, I randomize them, I use some repetitive values to create more points in those data sets. And now we have another data set that we can experiment with. So that's called cross-validation. It's not the training data, it's different from testing data. Cross-validation set is more of training the model and trying to find what's the behavior in cross-validation set. And if the working and accuracy and the model is fine, then we use it on testing data. There is a fine line between training with cross-validation and testing with cross-validation. I've given the definition so that you can have a better clarity, even though I've told you what's the difference and how it is used. So you can have a look at the definition. Now, we have gone through a lot of concepts till now. We have gone through, data collection, training splitting, outlier, feature extraction, feature scaling, which we'll have a look at later. Training the model, testing the model, feature selection, dimensionality reduction. All this is a part of a cycle that you need to do for training a model. First, we get the data collection. This is a starting point. We split the data into training and testing. We remove, we scale it, we do the feature extraction, we do dimensionality reduction, which is kind of scaling. We remove the unnecessary features. We train the model, and then we apply it on the testing model. Then we see what parameters need to be changed in the model, then we train it again, then we test again until we get a very good accuracy. Then we compare different models that, okay, is linear regression working fine or logistic or any other model? And then we deploy that model on a new data like we have here. So we have, well, 14, 15, we do all these techniques, and then we deploy the model on 13. So this is a full cycle of what happens actually. And you can see half of the thing is, more than half is actually just working on the data. It's just data manipulation we are doing. We are working on data pre-processing so much. It's mostly 60%, as I said before. Now there is one more concept which I thought I should teach you guys, which is bias variance trade-off. So I can see I've written the definition of bias for understanding that it's the difference between average prediction of our model and the correct value. Now that happens when we are trying to deploy the model on the testing set. When we deploy the model according to the testing set, we get some values. And then we compare these predicted values with the original values that we have already. Okay. And then we understand, okay, there is 70% accuracy, there is this amount of bias that we have in data. And variance is the spread, how data is spread across the data points. So I've told you with the plots how data is spread. So high variance is that, okay, data is good, we have a wide variety of data. And low variance is the clustered coagulated data. We can have an understanding better here. Low variance means the data points are coagulated, and high variance means the data point are spread across. This is low bias, this is high variance. So we can understand now that when we have coagulated data, our model doesn't know how to predict when the data point is outside the low variance data set. So suppose we have trained the model for this data points, and there is one data point which is maybe this corner. So our model won't know, like, okay, our model hasn't been taught that, okay, what about when the points are outside our data variation, So that's why we need high variance, so that our model can understand, our equation is versatile enough to understand what happens when it goes outside the data or with high variance data. So when the data points are too low variant, our models tend to underfit. And when there is too much of low bias, which means there is less error between predicted and true values, but the data set is high variant, it tends to overfit. Now you can see from this graph that it has high variance, okay? And the data points are spread across, and model is actually going from point to point. It may be like a parabola, but then it's fitting so much, it's overfitting than required. And because of high bias, that is based on equation actually, we have so many error between the predicted graph and the actual graph that we are using. Now this is good balance. We are getting a low bias, low variance plot. It happens a lot of time, and this thing is called bias variance trade-off. There is always something with bias or variance that you have to compromise to have a good balance between them. Not all data points are useful. Not all models you'll train would be best, or the most, like there is no room for improvement. That's not possible. We try to predict it. We cannot actually predict everything. So this is an important trade-off that you'll have to work on with experience it comes. And yeah, you can learn about types of error. It's actually very easy. I'll just maybe go through what you have to learn maybe. I gave you this link, right? It'll tell you about what is true positive, true negative. It has given the definition of what is true positive, false negative, true negative. Have a look at it. There are these types of error functions that we use to, understand what's the how the error, how the bias is varying across the data set. Go through each and every resource that I have given. Try to understand this code line by line. It's very important. You should have a thorough knowledge of what's happening. So this is data pre-processing using pandas, data visualizations, statistics, learning new libraries, scaling, outlier detection. Have a good read of all things I've told you today. These things would be used directly from next time. I won't be telling you what's with plot, training set, testing set, what is cross validation, why are we doing outlier, or what are the feature extractions happening. So have a look at it. And now we can go for question and answer round if you have any. You can unmute yourself and let me know. Okay, I can see something in that. Okay, it's for link. Yeah. Any doubts?
So actually, what is a validation data set? I was reading about it, but there's no implementation in real life.
Sorry, implementation?
Like when we write the code, we just write about the training and testing, right? What is the purpose
Yeah.
of validation?
Okay, so as of now, I haven't taught you in Python how are we implementing cross validation. But what happens is conceptually we have training and testing data set, and while we are trying to run a model, maybe a regression model, we use cross validation when we need to find um, the error, the accuracy when we are not having a lot of data points. So cross validation actually creates its own data set according to how many you want, using some points from training and testing. So there is a uniformity among the model. What there is an also possibility that your training set is actually a part of data points, which is like maybe so assume there is your training data set actually goes from 0 to 10, and your training set actually has data points from 100 to 10,000. So your model would be run on training data set, which has the values from 0 to 10. And then your model would be like, okay, you're getting good model on 0 to 10. And then you try to deploy that model on testing set. And testing set is actually from 100 to 10,000 data values. Like the values of the points are from 100 to 10,000. And then your model is like, okay, I don't know. I haven't been taught how to go for such high values. And there is a huge underfitting that happens. As I told you, you must have seen that line, which is underfitting. Now, what cross-validation does is that it takes some points from 0 to 10 from training data set. It takes some points from 100 to 10,000. It creates its own set, which is on which the model is run again. So this is where cross-validation can help. It creates more uniformity. It gives you more points to work on beside testing and training. So I hope it was a bit clear to you.
Yes, sir.
Okay. Anything else? Okay, then even if you have some questions, you can send me an email. It's in the notebook, or just ask me next time. It's time, I think, and thank you. And go through all the notebooks and source. It's gonna make sense to you even only if you are doing it yourself. And I hope you are learning. I'm not that fast. I just want to cover most topics, and there will be some conceptual gaps. Even I am confused with some things because there's so much to learn and so much mathematics and statistics. So go through the material again, go to the link, Google, and okay. See you guys.
Thank you, sir. And thank you all for attending this session today. And hope to see you soon on the day 5 of our workshop.
Okay. Bye.
Bye, sir.